Okay, many thanks, Carmen, for the introduction. Many thanks for giving me the opportunity. And my talk here today is kind of divided in two parts. First, I will report on work we did during the last 6 years on local structures in glasses, mostly with spectroscopy. And then at the end, I will give some further information on new possibilities here, not only on spectroscopy, but also on diffraction. And so let's start here. Before I forget this, this work I'm reporting on is based on works based on many groups that cooperated during the last 5 to 6 years from Potsdam, Dortmund, ESRF, as well as DAISY and other people as listed here. My talk will be, as I said, divided in two parts. In the first 2/3, I will talk about local structures in glass and melts. I will report on data from X-ray absorption spectroscopy, emission, and Xray Raman scattering. But I also include X-ray diffraction as a comparison and hope can convince you that we can end up with a common picture on this. And in the last part of the talk, I will briefly tease on the future high pressure X-ray absorption spectroscopy at the ESRF, as already introduced partly by Mohammed. And I will give you some further information on the upgrade work going on at ID27, where I'm actually sitting now here because we have beam time at the new ID27 from tomorrow on. Okay, why we're dealing with magmas and melts as Earth scientists, and everyone knows that volcanism is a very common thing to observe at the surface of the Earth, and all this volcanism that we observe and the associated plate tectonics are just surface expressions of the dynamics of the deep Earth in the interior as outlined in these cartoon here that shows all kinds of convection cells going on in the silicate part as well as in the metallic part of the deep Earth. And we can see that melts, of course, are ubiquitous at the shallower part, but they are also postulated for very deep parts of the Earth close to the core mantle boundary. And we know about these from seismic tomography, where we use the propagation of seismic waves to actually image the inner part of our planet, like we would do with X-ray tomography. And if we look into that, we can see that there's quite some spatial variation in wave velocities, and some parts of these very deep parts show negative anomalies in the wave velocities, as shown here in the lower graph. And they actually could be explained by the presence of silicate melts in these ultra low velocity zones, like they're just sitting above the core mantle boundary. So if these melts are really present there or not, there are a lot of questions coming up. What is actually their compositions, and closely linked to that, what are their physical properties, mostly density? Why are they sitting down there? Are they more dense than the surrounding? And of course, transport properties of these things are very important, viscosity, but also thermal and electrical conductivity, because this all controls basically the transfer of heat and energy within the Earth. And of course, closely linked to these properties are the structural properties. Are there any particular compressional mechanisms active that we end up with super dense melts that may be more dense than crystalline polymorphs with the same composition, or is just a compositional effect? And the compositions that we're mostly dealing with, and which have been already studied, are given by these rather complex composition systems. So a lot of magnesium and iron, but also calcium, aluminum, in addition to silica, which makes up more or less 40 to 60% or 70% of silicate melts on Earth. But also there are some studies purely done on the end member just to understand the mechanism of compression in these systems. If we look into silicate melts at shallow levels, shallow depths at ambient pressure, they are actually composed of polymery networks of SiO4 tetrahedra that are linked via their corners, and they build up a very loose network with lots of space, interstitial space, these ring structures that are then occupied by larger cations. We can replace silicon by aluminum, for instance, and to come up with quite some variation in this polymeric network that go from fully polymerized melts to fully depolymerized melts. So what kind of tools do we have to study non-crystalline systems, especially at high pressures and temperatures? And one way of doing this is wide-angle scattering or X-ray diffraction of non-crystalline systems, where we end up with a pair distribution function that gives us some insight to the local structures, to the correlation distances. But this information is a bulk information, and it's not element specific, and this may cause some problems in the interpretation, especially for complex natural systems. Other methods that we can use, especially for studying the local structure, is X-ray absorption spectroscopy in two flavors, either XAFs or XANEs. They give slightly different information, but basically we can learn about the local structure in terms of distances and coordinations. And there's X-ray emission spectroscopy, especially the valence to core part of this spectrum, that gives us some insight into the electronic structure, which means spin state and valence state, but also into some local structures. And then there is the indirect way of doing XANEs measurements, that is Xray Raman scattering, which again gives us the similar information as the XANE spectrum. So just some details on the techniques. If we do X-ray absorption spectroscopy, we basically measure the absorption coefficient across the sample as a function of the energy at a given excitation edge, K edge, or very often at K edge. And then the information that we want to get is in these wiggles or in the fingerprint that is produced close to the edge. We can do this in transmission. Yeah, just measure intensity before and after the whole sample and get the absorption coefficient from that, or we can measure it indirectly by using the X-ray fluorescence that is basically excited by this absorption process. The other less common techniques are X-ray emission and X-ray Raman scattering, and the basic principle behind it is outlined in these energy diagrams at the top. So if you do X-ray emission, you come with a high energy photon, you excite some core level electrons, and then the relaxation process is a specific energy. Here in this case, it's iron K beta energy. And if you measure these emission lines with very high energy resolution, you get some insight into our electronic structure as well as a coordination environment. If we do X-ray Raman scattering, this is an inelastic scattering technique. Basically, we also use a high energy photon, and then we look at the inelastically scattered photon that has lost some energy to the system to excite it. In this case, the example is the iron M edge, it's only 50 eV. And so this scattered photon will have an energy that is 50 eV lower than the incident one. And by this, we basically indirectly measure the iron M edge. And to do this, you have to do some work on your diamond emerald cells so you can really access this radiation. You need high resolution detection with analyzer crystals, either in this case for the Xray Raman scattering, or in this case with the von Hammer spectrometer. And the example shown here is a setup that we built up together with people in Dortmund at PO1 beamline at DAISY, where we actually combined these two measurement techniques. But they were also, we also did this already at ID20 here in, at the ESRF. So next slide. So a further problem that you encounter when you want to do a real X-ray absorption spectroscopy, especially XRFs, that is XRFs is not possible at high energies with normal diamond envelopes, so single crystal diamonds. You would end up with a spectrum shown here for the xenium KH at very high energies, which is basically dominated by all diffraction glitches, as we would say in spectroscopy. This was solved thanks to the invention of nanopolycrystalline diamonds that were invented by the group of Tetsuo Irifune in Japan. And with these anvils, you end up with a spectrum that is really nice and smooth and only contains information from the actual sample. This is actually the only way to really get high quality XRF data. The second problem that you encounter, if you want to work on low Z elements like silicon or calcium or whatever, this cannot be studied by X-ray absorption, although they're very important for especially Earth materials. So with X-ray absorption, I think you cannot work below 7 keV because then all your beam is blocked basically by the diamond envelopes, or you have to have very special envelopes. And so you can use this for high Z analog elements, or you focus your studies on high Z elements that are very often contained in natural magma as trace elements. In this case, we replaced silicon by germanium and calcium by strontium in these compositions that I'm showing down here. And you can already see that we end up with very nice XRF spectra that extend very long in K range. And the data I will be showing is first on a gamma knot glass, that is a germanium albite analog, basically a fully polymerized composition. So all tetrahedra are connected with each other, and this is possible because we replace part of the germanium with aluminium and compensate that for sodium. And then in the second step, we looked into germanium and strontium doped silicate glasses, which at first had the same composition as the first one. And then the second glass is something that is very similar or a simple analog of a basaltic glass. So first data set here, that is our data set on this germanium albite glass, so the gamma knot analog of albite. And you can see that we get a nice suite of XRF spectra up to K of 13 inverse angstrom that we can, that's shown here in K space and below the Fourier transform of it. And we were able to really get data up to 130 GPa. If we now do fit these data with a general ways of doing that, a relatively simple approach, the standard XRF fit, you end up with a fitted number of neighbors and a fitted germanium oxygen distance. And you can see that at low pressure, we have almost no effect, and that above kind of a few GPa, there's a strong increase of the germanium oxygen distance up to a maximum at about 30 GPa, and then we have a mere decrease. There's also some asymmetry in this germanium oxygen distance distribution, at least in this part. And if you look to the number of neighbors, it goes from something slightly above 4 to slightly above 6. And usually, as you see, as the error bars, the number of neighbors determined by XRFs is not very precise due to some inherent problems on the amplitude function. But the distance normally is very precise and shows mostly all the change in the structure part much better than the fitted number of neighbors. And if we now look what is actually happening to the structure, that is shown here by the fitted parameters, is that, and this is nicely illustrated by MD simulation done by Kaki et al. On basalt. So we go from our loosely connected silicon tetrahedral network to something that is much more dense. And in the first GPA, all this open space is normally collapsing until we have all the tetrahedra very close to each other, and we cannot go any further because we either we cannot shrink the tetrahedra; they are very stiff, and we cannot bring them closer to each other because we end up with a silicon-silicon or germanium repulsion. And this actually is the reason why we have a total rearrangement of the topology, so that we end up with octahedrally coordinated germanium or silicon and threefold coordinated oxygens instead of the twofold coordinated oxygen. And this is really required due to the oxygen bond valence sum, which would be violated if we would stay with this twofold coordination or a silicon tetrahedra. And it's also given by the silicon-silicon or germanium repulsion, because we cannot have, for instance, edge-sharing tetrahedra. So the tetrahedra become unstable. We end up with higher coordination numbers, in our case up to 6, and much longer metal-oxygen distances, and the longer metal-oxygen, or the metal-oxygen distance that we can determine image much more precisely what is actually going on in the structure when we use, especially Xray spectroscopy. But I think in general, we should look much more to the distances and not the coordination numbers. So we can now go a step further and look at the silicate glasses that we just doped with germanium. And this is given by the image on the left-hand side. And we will also compare to other data on the right-hand side. So on the left-hand side, we have our data set that I already showed. So that, again, the germanium oxygen distance as a function of pressure. And if we look at the same distance in either an albite glass doped with germanium or an albite diabsorbed glass doped with germanium, we end up with very similar variations, and also with a very similar compression at very high pressures. So is this system really different to other systems that had been studied before? And there is quite some work done on germanium oxide, both with EXAFs and with X-ray diffraction by the authors given here, Baldini, Hong, and X-ray diffraction by Kono et al. And we can see if we plot all on top of each other up to kind of 50 GPa, they all converge to the same variation. And only at very high pressures, the EXAFs data really level off down to lower distances, whereas the diffraction data stay at relatively high distance, long distances. And this is also shown by some of the EXAFs data already by Hong et al. And if we would now ask ourselves, what is actually the distance of germanium octahedra that is only compressed, and we can estimate this from crystalline germanium oxide and rutile structure. And if we just extrapolate this variation up to higher pressure, we would end up with this kind of line, which comes relatively close to what we observe in our glasses, in our germanium albite glass. So this is only germanium. We can go a step further and just look at the relative changes. So we normalize all our distance to the distance that is measured at ambient pressure. And then we can not just maybe get rid of some systematic differences, but also we can include silicon in this compilation, which is the green squares shown here. And the green squares and the light green squares, which is the data, I think the latest data set by Clemens Prescher et al. And we can again see that the germanium oxide and silicon oxide kind of converge to this upper trend, whereas all the others show a much stronger compression at pressures above 50 GPa. Then there's another line shown here. This is the one by Spiekermann et al., which was determined by a relatively, at that time, new technique, X-ray emission spectroscopy of the valence to core bands. And this is shown over here. So we have the K-beta 2,5 spectra of germanium compounds, and it's clearly shown that the spectra strongly depends on the type of ligand. And in a second step, if we would now start to compress, we would see that the energy difference between this K-beta 5 lines and the K-beta double prime line is changing as a function of pressure, but also the intensity ratio is changing. And this is due to the fact that these K-beta double prime is based on a very strong interaction of germanium orbitals with orbitals of the ligands, the oxygen orbitals. And therefore, it's really very sensitive to changes in the local structure. And Georg did a lot of work on this to kind of calibrate this and convert this into distances and coordination numbers, which is shown on the left, together with, again, some compiled data. And again, we have the comparison here on the right-hand side, and we can clearly see that also these germanium oxide data converge with in terms of distances, with the distances determined by X-ray diffraction and X-ray absorption spectroscopy. And to interpret this, we actually made up the case that first Georg did, but we also, in our discussion, we came up with the case that the two oxides are actually a little bit special because they end up at very high pressures with octahedral distortion, which leads to a less compressible structure in terms of distances. So there's not just a mere compression of the octahedral, but they're distorted. And if they would go to higher coordination numbers, they would actually increase again. And whereas all the other spectra or all the other compounds that we investigated, they just show simple mere octahedral compression to very high pressures, and this is rightly related to the more complex chemistry of these compounds. So we also replaced or put some strontium into our glasses to be able to look at a cation that is usually our network modifying cation if we think about the polymeric structure at low pressure. And this is data shown on strontium. I think it's the first data at all measured to such high pressures. And I'm showing here the example of the albite dioxide class. The EXAFS data that we are getting are not as long as in the case of germanium, due to some inherent problem with strontium EXAFS, but they are usable. And if we fit these data, we end up with a very slight increase also in the pressure range, where we see the conversion of 4-fold to 6-fold germanium. But it's not that severe. What we do observe in the fitted parameter that we go from a 6-fold coordination that is usually found for strontium and silicate glasses to a coordination number of 9. It's relatively high, really high. And this is kind of very simple, very similar to what is observed in MT simulation of basaltic compositions, as again, an example by Kaki et al., where we see the calcium coordination number that easily reaches numbers of 9 or even higher at higher pressures. So here again, experiment and simulation come up with a very homogeneous picture. So what about work at higher temperatures? So far I only talked about glasses, and of course in the deep earth we have very high temperatures, several thousands of Kelvin, and what is actually happening to our structure if we increase temperature is the structural transformation enhanced to lower pressures, or is it shifted to higher pressures? These are all questions that are still open. And for this, we were able not to record full X-ray spectra, but to record germanium Xane spectra. And shown on the left-hand side, you see basically the variation of the Xane region as a function of pressures at different temperatures. So room temperatures, 1600, 2000 Kelvin. And Maria, who actually did all this work, Maria Kostulovic, calibrated these changes in the Xane spectra to interpret these spectra in terms of coordination number. And we worked actually with externally heated diamond anvil cell up to 950 Kelvin, and at higher temperature we had to use a laser heating, and this was done at the old ID24 beamline. Maria, with his calibration, Maria basically looked at all the spectra that we measured and mapped out the coordination number given here either in color code or as the numbers, and we see a region where we're really in the glass below 1000 Kelvin. Yeah, this is all glass, and we can see that there's only a very slight difference between room temperature and higher temperatures. But if we then go to the melt, either in the really stable region at very high temperatures or in this region where we would also expect to have some crystallization, but the spectra shown here where we have ruled out that there's no crystallization, we see that there's a shift of the conversion pressure to lower pressures, roughly by 30%. So we would expect that the conversion pressure that we determine in glasses should overestimate the conversion pressure that we really would see at conditions of the deep Earth. So what can we do with Xray Raman scattering? And this is shown in the last two slides on the glasses. This is an example that was initiated by Sylvain Petit-Girard, and we were measuring the spectra at ID20 at the Xray Raman spectrometer. And you see here, again, we're looking with high energy X-rays, and we look at the inelastically scattered photon, and by this we can access either the silicon L edge or the oxygen K edge, and we could do this basically in the same run. Yeah, so you have the same sample at the same pressure and then measure the two edges. This takes very long, but we ended up with really nice spectra, as you can see. You can see that the spectra are changing as a function of pressures from this doublet to this singlet, and at low pressures we basically have the fingerprint of the quartz-like structure, and at the highest pressure we have a fingerprint that is very similar to the stishovite-like structures, and the shift here between the two spectra is only because the stishovite is recorded at ambient pressure. And to understand this change, and we see the same conversion, and that's the oxygen K edge, of course. And to understand this changes in the spectra, it's you can either do fingerprinting or you have a structural model based on molecular dynamics simulations. That's what we had, and this is based on the paper by Wu et al. In 2012. So we could simulate spectra, and they show not exactly the same spectra, but they show exactly the same relative changes as a function of pressure for both the silicon and the oxygen K edge. And if we would now go a step further and try to interpret these spectra in terms of changes in the structure, we can come up with these image on the right-hand side here, where we go from this four-fold coordination or two-fold coordination in case of oxygen, that is changing to a higher coordination, roughly at 20 GPa, but we not directly reach the six-fold coordination. There's an intermediate range where we have a mixture of five-fold and six-fold, and this is then basically completely converted to six-fold at about 60 GPa. Yeah, and the same is seen also for the oxygen, of course. And then at higher pressures, we basically stay in the six-fold range, but of course we can go further if we just increase pressure. You see further examples of this Xray Raman scattering in a talk later by Christian Sterner. So what is a big differences to the germanium system, I think, is that we can really detect this five-fold coordination that was also reported for germanium oxide, but we could not detect it, especially with our techniques that we use. It might be present, or it might be present at, of course, lower pressures. So with that, I'm more or less at the end of the first part of the talk, which I would just want to conclude here a bit, some take-home messages. So X-ray spectroscopy in either any way you can do, I think is a very complementary tool that provides element-specific insights to glasses and melts at high pressure and even high temperatures. And I believe we, at least for the conditions that we find on Earth, high pressure silicate melts are dominated by octahedral silicon and aluminium. And if we have germanium present, of course, also germanium. I think silicon oxide and germanium oxide are special cases due to the fact that we have only this highly charged small cations in this. And they really behave differently to more complex compositions at pressures above 50 kPa. This whole change in the structure is dominated or is controlled by not violating oxygen bond valence sums and not violating cation repulsion. And in the course of this work, we were actually brought to this theory of non-bonded forces that was developed in the 80s and is actually a very nice theory or a nice concept for understanding the different behavior of the complex and simple compounds that we studied here. And I hope I could give you some insight to the change when we go to high temperature to stable melt. And we are actually seeing that the conversion pressure of melts in the PT range that we investigated is lowered by 30% compared to the glass. And I think we can be quite confident that the silicate case would be kind of similar. So
Max, I'm sorry, I think we are running really out of time. I would like that it's possible that you conclude here, and we have time for only one quick question from the audience. Otherwise, I would like to ask the people to put the questions in the chat, and I would like to ask Max to keep an eye on the questions.
Okay, so I'm missing the second part of my talk, and I'm just going to the last slide, yeah?
Okay.
That is the new ID27 that we're starting to commission tomorrow, which gives a new possibility also for the looking at non-crystalline systems, and we will be able to do experiments at very extreme pressure with this very tiny beam. We will have double-sided heating either by YAG or through two lasers, and we will have time-resolved XRD down to possibly the microsecond timescale. And I'm sorry for extending my time slot. Thanks.
Thank you, Max. I'm sorry also that we are missing this second part, but if there is questions for Max, please keep an eye on or add them in the chat, and Max, please keep an eye on that. So if we can try to keep the time, the schedule, I would like to introduce the next speaker. Max, can you stop sharing your screen?
Yeah, I do. Thank
you. Yeah. So is Ilya around? So you can try to put the slides already on. Yeah, so I'm very pleased also to introduce our next speaker, who is Ilya Kupenko from the University of Munster, who is talking about some velocities on iron alloys that are potential candidates for forming the core planetary cores. So Ilya, the stage is yours.
So good morning, everyone. Thank you, Carmen, for introduction, and thanks the organizers for the opportunity to present our recent results that in large became possible due to the extremely brilliant source upgrade. So here is an outline of my talk. First, I will describe why we think that there should be some light elements in the core and how we can discriminate between them. Then I will go through the techniques, what are and were the limitations and advances, and then present some results on the effect of temperature, carbon, and silicon on sound velocities. So let's start with light elements in the core. As the deepest part of our planet is not accessible to direct sampling, all information about the composition of the core we can get only, or the vast majority of information about the composition of the core we can get from the interpreting the seismic observation. The core is mostly comprised of iron with some amount of nickel, but additionally it should host around 4–7–8% of light elements to account for the density deficit compared with pure iron and the density of the core. So here in brown, you can see the sound velocities and densities of the inner core, which are most reliably extracted seismic parameters, and blue lines show the velocities, densities of pure HCP iron. The ultimate goal is to find an alloy that could simultaneously match velocities and densities at core conditions. And the missing part is currently the temperature effect on velocity density trends. That is, in experimental work, is either mostly neglected or approximated, relying on huge extrapolation. The existing studies of temperature effect on sound velocities are mostly focused on compressional sound velocities, while the direct effect of the temperature on the shear velocities has been measured only for a very limited number of compounds and at relatively low pressures. Because of that, none of the iron light elements compounds up to now can fit the densities and velocities of the core. And these measurements are absent for a good reason. The experiments are extremely challenging and became feasible only recently owing to the major development in synchrotron techniques, particularly the extreme brilliance source upgrade. So now I will briefly explain the technique without going into too much details. So we utilize the nuclear inelastic scattering of synchrotron radiation. We are irradiating the sample and excite the iron nuclei that leads to emission of elastic and inelastic scattered radiation. The inelastic part of the spectrum is due to the vibration coupled transitions, and these transitions are related to creation and annihilation of phonons in the lattice. So from this inelastic spectra, we can derive the vibrational behavior of the sample and eventually sound velocities. One of huge benefits of nuclear elastic scattering, as many other spectroscopic methods, that it's ideally suited for monitoring of heating processes. So here, because it has the feature of the so-called internal thermometer. So here you can see the nuclear elastic scattering spectrum of iron silicate at megabar pressure, at room temperature, and at high temperature. So for any particular energy, the ratio between the created phonons and annihilated phonons is described by the so-called detailed balance law. So the higher is the temperature, the higher is the probability of phonon annihilation. And we can use this ratio to determine the temperature of these very atoms that are responsible for the signal. In order to get to high temperatures relevant for the core, we need to utilize laser heating in diamond angle cells for static experiments. That's the only way to get to core conditions. And many of you are familiar with the techniques. So you just squeeze material between a pair of diamonds and then heat it with a laser. In reality, situation is a bit more difficult, and it took several generations of PhD students of Leonid Dobrovinsky, including me, to construct a system that will be compatible with nuclear resonance scattering methods and to bring it to the current state of the art. Moreover, we had to develop special panoramic cells designed to optimize collection in the 90-degree geometry through the X-ray transparent gasket and still compatible with laser heating. Furthermore, to get to higher and higher pressures, we need to operate with smaller and smaller samples. And it makes problematic utilizing techniques with relatively large beam. So here you can see the typical temperature distribution in laser heated diamond angle cells compared to the X-ray size of the ID18 nuclear resonance beamline before the EBS upgrade. So as a result, we see the wide distribution of temperatures in the measured sample. So here I use example of Ms-Bauer spectroscopy just for demonstration purposes, where you can really see distribution of hot and warm material. For nuclear and elastic scattering, situation is even worse because we don't see individual contributions, but see one average picture which is dominated by low temperature components. And there is a workaround for this large beam, which we utilized before. We could use samples that are smaller than the beam and smaller than the laser spot, and then we don't have this temperature gradients. And that works relatively well for fast techniques like synchrotron Ms-Bauer spectroscopy. So it increased the counting time by 5-10 times, but if you need to collect the spectrum not within 10 minutes, but within 1-2 hours, that's still fine. But this would not work for photon-hungry techniques like nuclear elastic scattering, where instead of measurements of one spectrum for 8-12 hours, you will have to measure it for 1 week. So basically one spectrum per beam time, which is of course not compatible, not feasible. And thanks to the EBS upgrade, we now have the beam size compatible with laser heating at ultra high pressures. So here you can see the nuclear elastic scattering spectrum for the first time measured at within the core pressures and at high temperatures. So now let's move on to our results. So the effect of temperature, carbon and silicon on velocities. So first of all, why iron silicon carbon system? Carbon and silicon were both considered the major light elements of the core due to their high cosmic abundance, their affinity to iron during the core crystallization, and because the combined iron and silicon can cause the necessary depression of the melting temperature of the alloy, which is required to have the lower mantle solid, as we see it from seismological observations. Recent ab initio calculations propose that silicon and carbon combined can also match seismic observation. So incorporation of carbon should significantly reduce the shear wave velocities and increase the Poisson's ratio, while silicon will compensate for the density deficit. But there is the general discrepancy between theoretical and experimental results on the effect of carbon on core parameters. So some studies even suggest that iron carbide, Fe7C3, can by itself match both velocities and densities on the core. Yet I should note that these conclusions were based on the extrapolations of room temperature data measured at relatively low pressure up to 150 GPa. And in order to test these extrapolations, we investigated the temperature effect on velocities in iron carbide. So here you can see the nuclear elastic scattering spectra of iron carbide at 140 GPa and at various temperature. Nuclear elastic scattering is used to derive the density of phonon states, and which are close to zero energy, are dominated by acoustic phonons. Therefore, by extrapolating the reduced density of phonon states to zero energy, we can derive the average or mean sound velocity, or in other named Debye sound velocity. Then, combined with the other elastic parameters that can be determined from equations of state, we can calculate Vp and Vs compressional and shear velocities. So here you can see the resulting velocities in iron 7C3 carbide compared to preliminary reference Earth model. The common way to extrapolate velocities is to use the Birch's law, which assumes the linear change of velocity with density, regardless if the change of the density due to change of the pressure or due to change of the temperature. And we can see that for iron, compressional waves, indeed, in iron carbide, we can use this Birch approximation. So there is no difference between data measured at room temperature and at high temperature. For shear velocities, there is a minor temperature effect on Vs, but it more or less negligible. Yeah, so the high temperature data is plotted slightly below, but even when extrapolated to 5500 Kelvin, the effect is relatively small. The interesting observations is that Vs slightly decreases or does not changes with increasing density. That has been observed before in iron carbide, but the weak point here is the lack of proper thermal equation of state for this compound. So it was determined only to very minor pressures like 80 GPa and 1000 Kelvin. So that would be the next step to properly characterize this compound, is to measure its thermal equation of state. So after determining the temperature effect in a pure iron carbon system, we switch to iron silicon carbon alloy. So once again, you can see the density of phonon states and reduced density of phonon states from which we can determine the Debye sound velocity. And we complemented this study by room temperature compression data to determine the bulk modulus and density. So here you can see the Birch plots compared to pure iron and iron silicon alloy. So we can see that in comparison of carbon significantly decreases both compressional wave and shear wave. And to match the Earth's observations, we need to increase silicon composition to bring Vp higher up, but it will also send up the Vs, the shear waves. And we need more carbon-rich composition to match shear waves of the core, but that will move the compression waves further down. So they work in different directions, and we need to increase both carbon and silicon, and should have some huge temperature effect on shear waves to match the core parameters. And there is a problem with increasing carbon content even further and with determining the temperature effect. So we tried to investigate it, and we observed the composition of the sample to iron silicon alloy and iron carbide after heating at relatively small temperatures at around 60 GPa and 100 GPa. And we can say that this is not due to the reaction with diamonds, but really decomposition of the sample, because we see the reduction of the volume compared to due to loss of carbon. So to sum up, we investigated the temperature effect on velocities, which is small in iron carbide. In order to match the Earth's seismic parameters, we need a large amount of silicon and carbon with strong effect on shear velocity, with strong temperature effect on shear velocity. And such high amount of carbon is likely unstable in the alloy and leads to decomposition of the sample upon heating. So altogether, that allows me to suggest that silicon and carbon are unlikely presently together is the core composition. So with that, I would like to acknowledge all members of the team who participated in these experiments, in particular our students, so Susanna Müller and Yefim Kolesnikov, who are the main driving force of this project, but of course also our colleagues from Potsdam, from DAISY and from ESRF. And I would like to thank you for your attention.
Thank you very much, Ilya, for keeping up with the schedule. There is a time for a few questions, so please raise your hand and we will try to identify you as soon as possible if you have questions. Yeah, Guillaume, please.
It's just to start, you know, I push questions first. I was wondering regarding the temperature effect on the VS for this alloy. So your conclusion you say that the temperature effect should be the same as Fe73, because if you have a large temperature effect.
My conclusion is that we could not measure it because we see always decomposition of the sample. So even with very small amount of carbon, we see that carbon, if we heat at least below 100 GPa, that we always form carbide. Not form carbide, but it always decomposes to carbide. So the carbon doesn't stay inside the structure. And so we were not able to determine temperature effect because we measure then, so we cannot discriminate between two samples. We measure average between carbide and alloy with inelastic scattering.
Okay, I see.
That it will still remain in the structure if we go to even higher pressures, and we will try that. But from what I see now, it seems that carbon doesn't really like to be in the alloy. And maybe to add up to that, so if there is a temperature effect in the alloy, it should be way stronger than in carbide, because in carbide it's relatively weak. And to match the PREM, we need to have it like order of magnitude higher.
Okay, so if there is not any other further questions, any urgent questions, I would like to thank again Ilya, and we will move into the next speaker. Please keep an eye on the chat in case someone is, Paul Luber is asking a question. Probably you can ask the question in the chat, Paul. Could be that.
Yes, yeah, I was impressed by the thorough study. So your next step is to look for a third element, or you're still thinking of incorporating these two elements? What's your next step in progressing?
So yeah, the next step would be to try other elements, other combination of elements. It seems that single element will never match, but other terminals, yeah, that would be the next step.
Okay, thank you.
Thank you. So we can go into the next talk. I'm very pleased to introduce Angelica Rosa from the ESRF, who is going to talk about nanospectroscopy probes at the ESRF. Angelica, the floor is yours.
So thank you, Carmen, for this nice introduction, and thank you for having me here. Today I would like to discuss with you how we can unreveal deep secrets of planetary interiors with the extremely brilliant source and extreme condition nano X-ray absorption, fluorescence, and emission spectroscopy at ID24 DCM. Before I start, I would like to thank, of course, all the colleagues from the ESRF that are involved in this project. This is a collective work, and also the users that are involved, especially Guillaume Morat and Max Wilke. So let's start. First of all, I would like to highlight two pressing questions in Earth science, which are, for example, the formation and evolution of planets, which are not fully resolved for Earth, which, however, becomes a pressing question if we consider the vast amount of exoplanets that have been discovered in the last 20 years and the new possibilities to study the formation of planets and their atmospheres using, for example, the James Webb Telescope. This raises, of course, the question on the genesis of habitable conditions and how it is connected to planet formation. The second topic that is pressing in geoscience is for sure resources, critical elements. These are elements that we need for our high-tech industry that, however, will see a high delivery shortage most likely in future. And therefore, we need to find solutions to exploit these elements in a more efficient and sustainable way, also from our waste. Today, I will show you how experiments at the ESRF beamline ID24 DCM, double crystal monochromator, may help to give answers to these pressing questions. So ID24 DCM will now be transformed from an energy dispersive scheme to an energy scanning scheme, where undulator will be coupled uniquely to a monochromator and a KB system, which will allow to use combine this technique with high pressure sample environments to study very small sample volumes. So how can we get new insights into planetary formation using X-ray absorption spectroscopy? So here I really want to just show you very short overview of a planet formation on the example of Earth, what we know. So Earth has formed 4.5 billion years ago from the accumulation of dust forming planetesimals that grow further through impacts of meteorites, finally through impacts of giant planets forming a planet of Earth size that then differentiated and differentiated in the core, in a silicate mantle, and in a crust. Now, you see here that there is a very short time scale compared to the time scale of the life of Earth. So it's 120 million years. There are many key geological processes that happen in the interior of planets that really set the scene for how the planet will evolve and how habitable conditions, if habitable conditions can occur on a planet. These key geological processes are, for example, core formation, the entire melting of the mantle where a magma ocean forms, the mantle solidification, the crust formation, and concomitantly also the change of the atmosphere from a highly reduced atmosphere, a nebula gas-like atmosphere, to an outgassed atmosphere. Now, these key geological processes are very difficult to study because we have very few natural samples from such earliest times and is also of great depth. Most of natural samples come from 100 kilometers, and sometimes we are lucky, we find some that emerge from 600 kilometer depth. What we do observe are remnants of these geological processes that are actually differences in trace element compositions. And to understand now these differences that we can measure in the few natural rocks that we have, we need to understand the behavior of trace elements at extreme conditions. And there is where XAS can help us to unravel these deep secrets. So let me just tell you what are trace elements. So trace elements in geoscience are elements that are occur under high dilutions in the ppm to ppt range. So that means one atom per millions of other atoms. These highly diluted elements have no influence in the process, such as melting, phase transitions, or on the property of material. However, these elements have a high affinity due to their electronic structure to certain phases that can be, for example, an oxide, a silicate, or an iron melt. Now I want to give you one example where we can use trace elements to study a global geological process. So this is very interesting to use really the highly diluted elements on Earth to understand a huge, large-scale process such as core formation. So core formation took place in the early Earth's time, where actually a metallic melt segregated from a silicate, either solid or melt. Now, we can use the couple hafnium tungsten in geochemistry to understand this process, because these two trace elements have to the existing phases, the silicate and iron melt. And this couple also has a radiogenic daughter and parent isotope with a very short lifetime. That means that 182 hafnium decays in only 50 million years to 182 tungsten. And this is exactly the timing that we need for core formation. Now, what we do in geochemistry is to look at the tungsten isotope, its radiogenic produced isotope, and the stable isotope that is not added during geological history. And what we do observe is that the silicate Earth, so the Earth's rock from the surface that we cannot study, have a greater ratio than meteorites, which are the building blocks of Earth that have basically contributed to the mass of Earth. So this difference means that the stable isotope must have been incorporated into the Earth's core while it was forming. So there is a large consensus on this topic. However, what we do not know exactly, how fast was this process exactly. So we still have a high uncertainty on the timing and how this process was actually occurring. And this is mostly because most of studies are performed at relative low pressure conditions that are, for example, 25 GPa, and which is only 1/10, corresponds to only 1/10 of the radius of the Earth. The idea of ID24 DCM, or our goal, was to extend now this observable pressure and temperature range in order to allow to study the trace element behavior at a large range of pressure, temperature, composition, and oxygen fugacities. Now, what I showed you here is just one example of one geological process where we can use trace elements. There are, of course, many other geological questions that can be addressed with trace elements. And this will be possible to address at ID24. So what challenges do we have to face? So what we tried to tackle at ID24 in the last few years is to conduct experiments at extreme conditions, at high dilutions in the ppm range. As we can see here in this graph, most of elements on Earth are actually at high dilution levels, are below even the ppm range, and to study samples that are chemically complex, where we have two coexisting phases with differences in concentrations of samples. And here, X-ray absorption spectroscopy and fluorescence spectroscopy is an ideal tool because of its element selectivity and concentration sensitivity. So just very quickly, we can see from XAS how an element is incorporated, if it's in a gas phase, in a liquid, or in a solid, already just from its signal. We can also probe the local bonding environment, the number and sort of neighbors, its electronic state, its valence, orbital splitting, and the concentration of an material of an element in a material using X-ray fluorescence. Now, because of the vast interest in this technique from the user community, the high pressure or extreme condition XAS was developed at the ESRF already at 2012, 10 years ago. And about 40% of the beam time was dedicated at ID24 BM23 to this operation mode, not only for science, but also for material and physics, material science and physics. And there is a talk of Virginia Monteseguro that will give us some aspects of this technique for physical problems. Now, before EBS, we were able, for example, at ID24 to conduct time-resolved microxenes studies in the laser heated diamond anvil cell covering the lower mantle conditions. However, in these studies, we were mainly limited to major elements and we could not access the XF signal. Therefore, the bonding environment of these elements were not fully constrained. At BM23, in turn, we could acquire very high quality XF data. However, we were limited in the temperature range and also in the dilution levels that we could reach. Now I just want to point out it is very important to study trace elements at their relevant dilution levels, because only like this we ensure that they do not influence the properties and the observed processes. During this time, we already acquired data on trace elements, and I would like to give you just a few examples from my research where we really pointed out that the behavior that we observe at ambient condition or at shallow depths do not always correspond to the behavior of a trace element in the deep Earth interior. I want to show you this on the example of noble gases here, krypton, where we studied the compression behavior of krypton, where we showed that noble gases have a high compressibility and they reduce their size to 50% of the atomic volume already at the core mantle, at the upper and lower mantle boundary. So this high volume reduction may have strong consequences on the distribution behavior of noble gases. And indeed, in a later study, we could show that noble gases actually could likely be incorporated in solid lower mantle phases such as ferropericlase and bridgmanite, which is counterintuitive because at shallow depths, most studies are actually showing that noble gases are more likely incorporated in silicate melts. We also, as Max Wilke already showed, investigated why actually why melts are not anymore likely hosting noble gases, and where we could show that melts undergo a very strong densification mechanism in the lower mantle, which may be the explanation for these observations. So just to sum up, before EBS, we were able to cover already a large pressure temperature domain for studying trace elements or major elements, however, mostly at weight concentration levels. There was only a very small pressure temperature domain that we could actually reach in addition high dilution levels. And with the EBS, with the upgrade, we will now be able to study trace elements at their relevant high dilution levels and at a very large pressure and temperature domain. Of course, these kind of studies are highly complementary to dynamic compression experiments on major elements that will become now possible at high power laser facility, and I refer here to the talks of João Alexis Hernandez and Rafaela Torchio. So here are the new capabilities of ID24 DCM and BM23. So these are two micro X-ray energy scanning X-ray absorption spectroscopy beamlines. Both of them will cover a large energy range, 5 to 50 keV for XRFs, but also for emission fluorescence spectroscopy, slightly shorter range in energy, where we can access a large K range and achieve a high energy resolution. ID24 will feature a sub-micron beam size, while BM23 will give a very further reduce the beam size to 2 by 2 micron. The flux at ID24 for energy scanning scheme has increased by orders of magnitude, while at BM23 we observed an increase of flux by an order of 2 to 3. Both beamlines will allow quick XRFs measurements. At ID24 we plan to achieve 1 XRFs in 1 second. And of course there will be, as I said, X-ray fluorescence and emission spectroscopy possibilities with high spatial resolution. Both beamlines will profit from an ESRF-made monochromator that will feature unprecedented performance with an extremely high position and energy stability and reproducibility, which is ideal for long acquisitions on highly diluted samples, time-reserved studies, and if we have to change energy, for example, for different X-ray probe techniques. ID24 will open this year, and BM23 is open since last year. At ID24, we are now in the last stages to finalize the laser heated diamond anvil cell setup. that will allow us to reach extreme conditions beyond the Earth's lower mantle, that will combine actually different X-ray probe techniques, absorption, fluorescence, and emission spectroscopy, as well as complementary diffraction. So we actually, there was a huge investment to make actually a large open space to add here a von Hammer spectrometer that was developed at ID20. We also really worked on the complementarity of the setup to ID27 in order to allow users to acquire data on both beamlines that can be compared and therefore allow for very robust results. Here we will also exploit the high flux that will be featured by the EBS and to actually investigate how trace elements behave at high dilution levels. This setup will also comprise a T gradient mapping setups that will allow to better understand partitioning and melting experiments, as well as a pulsed laser heating system that is currently developed in collaboration with geomaterials. Here is also one aspect that I would like to highlight. Of course, for understanding trace element partitioning, it is very crucial that we understand the thermal gradients, the distribution of temperature in these small heated sample volumes. And here, actually, this is a joint PhD thesis supervised by Guillaume Morat, by Nicolas Jesel, who actually conducts finite element modeling to understand better these thermal gradients in different samples. That I show you here on a 2D map that has been measured, for example, on a sample by Du et al. Now we will also have new detection systems for these different probe techniques, of course, at ID24 and BM23. So we will have a polycapillary that we can, for example, combine with a resistive heated diamond cell or with a Paris-Edinburgh press to really extract a signal from our sample volume and reduce the background. We will have a new, we already installed a new X-ray diffraction detector with a very high dynamic range that allows us to study very weakly scattering samples next to the diamond peaks. We will also implement a crystal analyzer system that is implemented already at BM23 that will now be transferred to ID24. And a von Hammer system to combine a micron and a nanobeam with these X-ray emission spectroscopy probe techniques and high pressure, high temperature devices, which ultimately allows to study very highly diluted samples in an unprecedented way in terms of the electronic and atomic structure. So we will have a major gain in energy resolution, spatial resolution, and the dilutions that we can achieve. Just to give you one example on actually what will change with ID24 DCM, here I show you an example from Stechan and Wilke et al. On measurements of zircon concentrations in fluids, the heated and pressurized to rather moderate conditions. What could be achieved at ID24 is to measure concentrations down to 75 ppm, while Xane studies were only possible to 180 ppm, but there was no possibility for XAFs. At ID24, we will be able to push these limitations, and we will be able to study such samples also using XAFs and at higher dilutions, and of course at higher pressure temperature conditions. There will be also, of course, the possibility to adapt a new diamond envy cell technology to reach multi-megabar pressures for users and to adapt these diamond envy cells with different X-ray probe techniques. And with this, I want to thank you for your attention. I'm happy to take your questions. And if you want to have a look on geoscience activities from ESRF researchers, I invite you to take a look at our new website, where we give you some news, research highlights, in-house activities, and experimental platforms. Thank you.
Thank you very much, Angelica, for the interesting talk. So if there are any questions, please raise your hand. We have time for a couple of quick questions, Angelica. Okay, probably I have one question, Angelica. In the new capabilities for ID24, you mentioned the limit of temperature of energy will be 4 kV, if I understood, 40 kilo electron volts. do you think that will be a limitation for some of the interesting trace elements, the heavier ones, to work on some of the KHs, but are the LHs sensitive enough for this analysis?
Yeah, also this limitation is mainly due to the optical scheme, because we need to do we use platinum mirrors to focus the beam, and therefore we cannot go to higher energies. However, we did already experiments on LHs for elements that are heavy, for example, rare earths. We did a lot of work, and these kind of elements can be similarly studied. And yeah, of course, the signal is lower in terms of intensity, so we might not go to the highest dilution levels as for the KHs.
And do you have an estimate of what will be the enrichment that you need to have a sensitive enough analysis, or what is the order of magnitude in general that you need to go to?
So we did some experiments on rhenium L3H, for example. For now, at BM23 or at BMD beamlines, we could actually see like XF's or Xane signal down to 100 ppm. So I think there is, yeah, we did not test yet, of course, how far we can go in dilutions for these elements at ID24, but we are planning just now a test experiment at BM23 on these edges.
Okay, thank you, Angelica.